Hello, and welcome back to the Cosmic Companion. This week, we are happy to be joined once again by Dr. Stephen Daunt of the University of Rhode Island. He recently led a study of reviving microorganisms that lay dormant under the ocean floor for over 100 million years. His work could rewrite what we know about life. Also, in this episode of Astronomy News with the Cosmic Companion, we take a look at the discovery of a world much like Saturn, orbiting a nearby star, and we see how storms on Jupiter alter the atmosphere of the largest planet in our solar system. Finally, we talk about a unique study that used the Hubble Space Telescope to examine the atmosphere of Earth during a lunar eclipse, testing methods to find life on other worlds. An exoplanet the size of Saturn was found orbiting a star just 35 light years away from Earth. This world was found by astronomers using the Very Long Baseline Array network of radio telescopes by measuring tiny movements in the star created by the gravitational tug of planets on their parent star. This is the least used of the 5 major means of finding worlds around other stars, but this technique, called astrometry, holds great promise for future discoveries. The Juno spacecraft orbiting Jupiter recently revealed secrets of the Jovian atmosphere with findings on the nature of these mighty storms of Jupiter. The spacecraft, launched in 2011, found ammonia can join with water in the upper atmosphere of Jupiter, forming half-frozen mush balls, which then fall down into the atmosphere before warming. This process could account for unexpectedly low concentrations of ammonia seen in the upper atmosphere of Jupiter, researchers believe. Juno will continue to study Jupiter until July 2021. When engineers will send the vehicle plunging into a suicide dive into the massive planet, avoiding possible future contamination of the Jovian moons. The Hubble Space Telescope is normally used to peer deep into space. However, a new study used the famous Space Observatory to study the atmosphere of Earth. The perfect alignment of a lunar eclipse in January of 2019 allowed astronomers to view light from the sun which passed through the atmosphere of the Earth before being reflected by the moon. By detecting ozone in our atmosphere, researchers showed how this gas, usually associated with biological processes, might be seen on distant worlds which pass in front of their parent stars as seen from Earth. On next week's episode of this show, airing August 18th, we will talk to Dr. Allison Youngblood, who headed this unique study. Make sure to tune in. This week, we are joined by Dr. Stephen Daunt of the University of Rhode Island. He recently reanimated organisms which had lain undisturbed for more than 100 million years. This week on Astronomy News with the Cosmic Companion, we're happy to welcome back Dr. Stephen Daunt, from the University of Rhode Island. He recently made a fascinating discovery about life forms underneath the ocean floor. Welcome back to the show, Stephen.
Thank you very much, James. It's a pleasure to see you again and speak with you.
Fabulous. So just tell us a little bit about what it is that you found that was so interesting.
Okay, I want to start by saying that by mentioning that Yuki Morono is really the champion of this study that came out this week. He led the project and did a great job, and I was fortunate to be part of it. But what we discovered essentially was that these microbes that have been isolated under starving conditions for 100 million years wake up and party when Yuki gives them a buffet. So
I want to go to one of this guy's parties.
What was that?
Said I want to go to one of this guy's parties.
Yes, absolutely. So these microbes have been buried. They're in 100 million year old sediment, and there's not enough energy for them to swim anywhere. And the sediment is really fine grained, and so they can't really slip between the cracks. They really have been isolated since the sediment was deposited 100 million years ago. And there's very, very little for them to eat. There's so little for them to eat that calculations that I've done and that other people have done suggest that there's barely enough energy available for them to keep repairing their bodies as molecules break. And yet they're still there after 100 million years. And so what Yuki did when we recovered a sample of this sediment, he split the sample into little pieces, and he offered those pieces different isotopically labeled kinds of food, like acetate, which is something that's used to make plastic, and it's also something that's common in vinegar. And he'd offer them amino acids, things like proteins are made out of. So he offered them a variety of things, and what he found was that all of these microbes would eat those things beginning fairly quickly, and they would begin to grow. They would incorporate the isotopes into their bodies that he'd given them, and then they would divide, they would reproduce, they would multiply. And so what he essentially showed literally was that microbes locked away under starving conditions for 100 million years will shake it off and build their bodies and multiply using a variety of food sources if you give them the opportunity.
Wow. So how do we know, do we know anything about what kept these things alive, if dormant, for all this time?
Well, there's a very slow trickle of energy, and we don't really understand biologically how something can survive 100 million years under those conditions, because the rates of reaction that they're relying on are many orders of magnitude slower than anything that happens in a laboratory. When someone's growing E. coli, they get energy fast enough that they can be dividing every few minutes to every few hours. In sort of a natural environment, people have done these really challenging experiments with organisms that eat sort of nitrogen pollutants. And it takes them years to get those experiments up and running. And those are natural communities that live in the surface world around us. Okay. So the idea that you could get something to grow after 100 million years, verges on extraordinary.
Yeah, absolutely. So are these organisms anything like anything we're familiar with at all?
That's a really good question. And the short answer is that there's 10 different categories of organisms that all woke up and joined the party. They're almost all bacteria. They're all organisms that are well known from the world around us. They're basically marine organisms. So there's not a lot of what I'll call phylogenetic novelty there. I mean, these aren't unknown organisms in the broadly defined categories of things. So they might be unknown or previously undiscovered variants of known things. So it'd be like, it's like when people discover something new in the rainforest, they'll say, we found a new kind of monkey. And you can look at the monkey and you can look at the photos of its cousins and you can say, okay, yeah, I can accept that's a new monkey. It's got a red face. But it still looks like all the other monkeys pretty much that it's related to. So the things that Yuki pulled out of the sediment, they're pretty close relatives of things that live in the world around us. Which leads to the interesting thought that they may not have unusual capabilities.
Right.
It could be that you could bury for 100 million years all kinds of microbes, all kinds of bacteria, and resurrect them. But 100 million years is a long time for a graduate project. So
Defending that dissertation would just take forever.
that's right. So we kind of have to do it in reverse, just go out and take different samples of 100-million-year-old sediment and see what comes up. But what he got out of that sample was pretty diverse already. So that suggests that there's a pretty diverse range of things that can survive under those conditions.
So how'd you go about it? How'd you find this out?
Well, this was an international expedition that Fumio Inagaki and I led. And we deliberately went into the South Pacific Gyre because it was the deadest part and is the deadest part of the ocean. There's the least productivity in the surface water of any part in the ocean. And the flux of organic matter to the sediment is really low. And the sediment accumulation rates are so slow that it might take 10 million, or let me step back. It might take 1 million years to get 10 centimeters.
Mm-hmm.
So this much sediment might take 1 million years to accumulate at some of these sites. At the site where Yuki took those really old microbes out of, the sediment's accumulating at about 2 feet a million years. That's really low. I mean, like a dedicated 10-year-old can pile up 2 feet of dirt in no time at all, right? But here we're talking about the world's biggest sweep of ocean floor, and the sediment's accumulating really, really, really slowly. And there's this idea that goes back 60 years that there are no microbes living in that sediment deeper than 1 meter or 2. And there's another idea that goes back decades that oxygen disappears once you're 1 centimeter or 2 or 3 or 4 into the sediment. And so when Fumio and I led that expedition, we wanted to test those hypotheses because I thought there was pretty good indirect evidence that oxygen went all the way through. And so we went out and we found that, in fact, oxygen does go all the way through to the rocky basement below. So you might have 70, 80 meters of oxic sediment. And we found from Yuki's work and Jens Kallmeyer's work, who was another member of the expedition, that there are little populations of cells all the way through the sediment. So once we walked off the ship, we knew we had organisms and we knew that we had an environment where they might be able to breathe oxygen. But we didn't know who the organisms were. We didn't know what they could do. And what Yuki's experiments have shown is who they are and what they can do.
That's pretty fascinating. So, what is life like? What are the conditions like under the floor there? What is life like for these?
It's really, really fine-grained sediment. So the individual sediment particles by definition are clay size. So they're essentially 0.002 of a millimeter or smaller in diameter. And the main component of the sediment is a mineral called zeolite, which is this poorly ordered aluminosilicate mineral that's very soft and easily smushed. And our friend Rick Murray, who was on the expedition, did extensive tests with his students at BU, and they determined that zeolite is basically altered volcanic ash to a first approximation. So we're looking at 100 million years of really slow occasional fallout of volcanic ash turning into this zeolite mineral that then traps the microbes. And just to give you a sense of how slowly this accumulates and knowing your audience, this sediment accumulates so slowly that if you run a magnet through it, you will pull out nickel iron micrometeorites. Because there's a constant rain of micrometeorites from the universe. And in most sediment of the world, you never find them because other stuff accumulates so quickly. But in this abyssal clay, the sediment accumulates so slowly that any given piece of sediment you can pull a micrometeorite out of. And this was discovered by the Challenger expedition around 1870, who were the first people to dredge this clay. And so when I take expeditions out to that part of the ocean, I toss magnets at the young scientists and I tell them, find me a micrometeorite. And then, of course, they all get really happy because they just found their first micrometeorite.
Wow, that's amazing. And so these volcanic deposits, are they put down by remains of volcanic eruptions that happened on the land and wound up underwater through continental drift? Or could this have also have occurred from underwater volcanoes?
No, to a first approximation, it's aerial volcanoes. So it's stuff on land that blows ash into the atmosphere, and then that ash circles the world and slowly falls out. So given the prevailing winds and sort of the nature of volcanoes in the southern hemisphere, probably the primary source is the Andes, but the winds go toward the east there at those latitudes. So that ash gets blown into the air off the west coast of South America, and then it circles the Earth, falling out as it goes. And by the time you get to the South Pacific, there's just a little bit of it left to fall out.
Right. I remember, remember when Mount St. Helens erupted, and I was in New England and still being, the other side of the country. I could taste ash in the rainwater a couple days later.
My family lived in Yakima, Washington at the time of eruption. I was in California, but my parents were in Yakima. And I remember my father calling me and complaining because he had to shovel the ash off the roof. They got a couple inches of ash on the roof, and he was worried that if it rained, it would collapse the roof.
Right.
So he'd get up there with his snow shovel and shovel the ash off.
Wow.
But it's like you saw in New England. You didn't get very much ash in New England. He got a lot in Yakima.
Right.
Imagine you go all the way around the world. By the time you get to Siberia, there's even less than in New England.
Right. It's pretty amazing. So what's the next step that we can take to try to study these dormant little creatures?
So for me, a really important step that frankly is not a step I'm likely to lead the effort on is understanding what are the mechanisms that allow these organisms to survive like this. Because they're essentially violating our sense of what's acceptable, right? They are living for 100 million years on barely enough energy to keep repairing their molecules. And this means either they are multiplying without enough energy for our calculations to allow them to multiply, or they're living as individual cells for like 100 million years. So Francois Jacob, who is a French Nobel laureate, used to say that science is the art of distinguishing what's actual from what's possible. And his idea was you imagine what's possible and then you sort through the options to determine what's actual. And the thing that I love about study of life beneath the seafloor is that it violates our sense of what's possible. That what's actual actually forces us to expand our understanding of what's possible. That either microbes can live for millions of years or tens of millions of years without dividing, or they can persist and divide on many orders of magnitude less energy than we currently believe can be true.
Wow. That's amazing.
And so a big next step is figuring out which of those two answers applies.
It's amazing. And so, of course, one question that I'm sure is on everyone's minds, with everything going on in 2020, which has so far pretty much been a disaster a month. You came across some creatures which had been peacefully sleeping for 100 million years, and you decided to go poke them with a stick and wake them up. Was that really such a great idea, Steve?
Yeah, we think it was a great idea. And I'm going to begin by defending Yuki, who led the study, just so you all know he took proper precautions. This work was done in an ultra-clean lab at an ultra-clean bench. And so they set up a lab and a workbench that essentially guaranteed that they would have fewer than one microbe, fewer than one cell per, say, liter of air in the environment. So it's a very, very controlled environment. Now, the reason they did that was because we wanted to be sure we weren't contaminating our results. But it also has the benefit of not letting the organisms get out that we're studying. Having said that, I don't want anyone to worry that even under extraordinary conditions, there's any risk that these things will get out and attack the world. These things have been buried for 100 million years. This is roughly 100 million years longer than there have been people on the planet. So these organisms are not in any way co-evolved to attack people or any animals that are living today. That's the first thing I'm going to say. The second thing I'm going to say is that they're basically normal marine organisms at some level. And marine organisms, by and large, don't attack people. They're not really pathogens. There are pathogenic things in the ocean that attack things that live in the ocean. But it's not a really good strategy to sit around the ocean waiting for people to attack. So organisms that live in the ocean are not typically things that can get on land and take advantage of people. There are extraordinary, well, I shouldn't call them extraordinary, there are sort of common circumstances where pathogens get into the water. So like if you live in Los Angeles or Rotterdam and your sewage outflow is going into the harbor, into the Pacific Ocean or the North Atlantic, then the pathogens that come out of people's bodies enter the harbor. Right. So if we were digging up harbor sediment from yesterday, there'd almost certainly be human pathogens in it. But normal marine organisms don't attack people. And these are essentially normal marine organisms that have been buried for 100 million years. So we don't have any real concern that they will be a risk.
Super. It was great talking with you again, Steve. Hope to have you on the show again sometime.
It's been a pleasure. Thank you very much for inviting me back, James.
All right. Super. Take care.
Take care.
And that was Dr. Stephen Gaunt of the University of Rhode Island.
Next week on Astronomy News with the Cosmic Companion, we'll be joined by Dr. Allison Youngblood of the Laboratory for Atmospheric and Space Physics, who led the recent study using the Hubble Space Telescope to study ozone on Earth. We'll talk about her work, what it's like to use the Hubble Space Telescope, and we'll discuss the search for life on other worlds. Please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of Astronomy News with the Cosmic Companion, please download and share the episode on YouTube, Facebook video, or on any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.